Okay, we're in tutoring with Mr. Schmidt over some solution problems. We're going to go through these fairly quickly. Um, so hopefully in about 15 minutes we'll be done. But just realize 15 minutes could save you 15% or more on your next quiz. So the first part we're going to have is a solution is prepared by mixing 17 grams of sucrose with 183 grams of water. We should recognize that sucrose is a solute, whereas this water is the solvent. And together, this makes the solution. So it's very important to understand what the solution is, what the solute is, what the solvent is. It is also equally important to understand that percent mass, or percent by mass, is equal to the mass of the solute over the mass of the solution. And you're going to multiply that times 100%. That's what gives us a percent mass. So, or you can say that you have your mass of your solute, which is going to be mass of sucrose over the mass of sucrose plus mass of H2O times 100%. And so the mass of sucrose, 17 grams. The mass of the solution, or mass of the sucrose plus water, 17 plus 183 is 200 grams. And you multiply that times 100%. Now we knew if 17 was over 100, that'd be 17%. But 17 is over 200, so it's going to be half of 17%, or 8.5% by mass. Now it wants to know what is the concentration expressed in parts per million. So parts per million is going to give us, the formula for this is the mass of the solute over mass of the solution times 1 times 10 to the 6. And so we can see that it's very similar to this expression right here. And so 17 grams over 200 grams times 1, not know how to change color on me, times 1 times 10 to the 6, and you should get something like 85,000 ppm, parts per million. And that just means that when you have 85,000 grams of the solute, or sucrose in this case, you should have 1 times 10 to the 6 grams of the solution. So that's all that means. The next part, St. Louis, they have some fluoride in the water, so they have some good teeth. And if you have a 750 gram sample of water with this concentration, and it is measured how many grams of fluoride ions are present in this solution. So they're showing you 750 grams of water, but also recognize they're saying solution. So this is water with the fluoride ion in it. So it's 750 grams of the solution. So when they say water, this is water plus the fluoride ion, which makes the solution. This is solute plus solvent. It's water plus the fluoride ion. And so if we know that we have 0.99 parts per million, that means when we have 0.99 grams of fluoride ion, we have 1 times 10 to the 6 grams of the H2O solution, right? And plus fluoride ion, or we can call that the solution. And so it's going to be very easy to relate this conversion factor to what we already know, relate what you know to what you don't know. So we don't know what the mass of the fluoride ion is in this situation, but we do know the mass of the solution. which is 750 grams. And I'm just going to put solution here. They're calling it water, but it's the water fluoride ion solution. And we know that when we have 1 times 10 to the 6 grams of this solution, that we have 0.99 grams, or really close to 1, fluoride ions. And so then this just simply becomes a simple math problem, and you get 7.425 times 10 to the negative 4 grams of the F1 minus. So that is a very small amount, and that's what you would expect if you had 750 grams, maybe a small cup of water, and you wouldn't be drinking a whole bunch of fluoride. It's going to be very small concentration of fluoride in your water, and that's all you need to help strengthen your teeth. So let's go to the next one. How many grams of precipitate will form when you have 100 milliliters of this 0.4 molar silver nitrate solution, and it is added to 75 milliliters of a 0.23 molar potassium chromate? So the first thing we're going to have to do is figure out what the balanced equation for this reaction is. So we're going to take silver nitrate, AgNO3, plus potassium chromate, K2CrO4. And you should know the charge of silver is 1, nitrate is -1, charge of chromate is -2, charge of potassium is +1, so we need 2 potassium for 1 chromate. We should recognize this is a double replacement reaction because we have two compounds. And so silver is going to, this is double replaced, silver is going to go with the chromate. So it's going to be Ag2CrO4 plus KNO3. And because we know our solubility rules, that's CrO4, we should know that chromates are very slightly soluble. They're not soluble except for when you're with the alkali metals, because alkali metals are, everything with alkali metals are soluble. So this potassium and chromate, that will be soluble or aqueous. This is aqueous, all nitrates are aqueous, but chromates are not. And since it's not with a alkali metal, this is going to form a solid. And we also know alkali metal and nitrates, that's always going to be aqueous. So it's a no-brainer. So this is going to form our precipitate or our solid. Now the next part is determine the number of moles in each solution. So we have to do that for AgNO3, and we have to do that for not potassium nitrate, potassium chromate, K2CrO4. And so this is simple enough. We should know that 100 milliliters is equal to 0.1 liters. We should also break this value up into 0.4 moles per 1 liter is equal to 0.4 molar. So we're breaking that up. Now we know the volume, we know this ratio here, we just don't know the number of moles. So all we have to do is use this and this. So we have 0.1 liters. 1 liter is 0.4 moles. And our answer then is 0.04 moles of the AgNO3, silver nitrate. The next one, we're doing the same thing. We should know that 75 milliliters is 0.075 liters is equal to 75 milliliters. We know it wouldn't be 0.75 because that's 750 milliliters. And then we should also know that 0.23 moles in 1 liter is equal to a 0.23 molar. Ooh, that's not good. 0.23 molar solution. So once again, we take the volume, use the molar expression when broken up to relate back to moles. So you have 0.075 liters. 1 liter is equal to 0.23 moles, which is going to be equal to to 0.01725 moles of the K2CrO4. All right. Oh, one thing we forgot to do, which Shell would have reminded me, was to balance this equation. We sure have not balanced that yet. So we got to make sure we balance this before we move on. We did write the equation properly. We just simply did not balance it. So we want to do that real quick. Of course, I need to fix some items here real quick. Go here. Yeah, get my pen showing back up. And so there's an easy way to kind of determine what our limiting reactant is going to be. If we multiplied both of these values times 100, what we would get here, and this is just a simple way of doing your stoichiometry, what we would get here if we multiply this times 100 is what we get 4. If we multiply this times 100, we get 1.75 or 1.725. And so if we take, well, we still haven't balanced, so let's balance this real quick. Let's see, we need 2 silvers, we need 2 nitrates, and I believe we are balanced now. So if we take 4 is 2 times this value, we would get 2 times the solid, or 2 moles. So silver nitrate will produce 2 moles, whereas if we take this value, 1.725, this is a 1-to-1 ratio, so that means we would get 1.725 moles of the silver chromate. And since 1.725 is less than 2, this is our limiting reactant. And so that's just a real quick way of analyzing it. Otherwise, you would have to put both of those into a bracket and then use their stoichiometry. And you can do that. And so what they want to know, though, is how many grams of the precipitate, not the moles. It's easy once we determine the limiting reactant. To do that, all we have to do is get the molar mass of this silver chromate, which is 331.74 grams per mole. And to show you the long way of doing what I just said, what you can take is your values, and we know that we have 0.04 moles of the silver nitrate. And we know that 2 moles of silver nitrate is equal to 1 mole of silver chromate. And if you want to go ahead and find the mass, 1 mole of silver chromate is equal to 331.74 grams. Ag2CrO4. And so we plug that in to our calculator. And I didn't do this calculation already, so I'm going to have to do this now. You should get somewhere around 6.6 0.63 grams of the silver chromate. And if you go the other route, we have 0.01725 moles of the Ag2CrO4. And this is a 1-to-1 ratio. And this is largely why I didn't do that other calculation, because I already knew this was the limiting reactant. So 1 mole of Ag2CrO4 is equal to 1 mole. Oh, I said that wrong. K2CrO4. K2CrO4 is equal to 1 mole of the Ag2CrO4. And then 1 mole of Ag2CrO4 is equal to 331.74 grams. And so when you do this calculation, you get 5.71 grams of Ag2CrO4. And like I said earlier, this was the limiting reactant. We could tell, even though we multiplied these values times 100, it just made it easier to use these fractions and determine what the limiting reactant was. And at that point, all we'd have to do is convert this number of moles to mass using the molar mass, and we would have gotten 5.71 grams, because this is our limiting reactant, potassium permanate. And I believe we answered the question. Let's go back and how many grams of precipitate will form? The precipitate was silver chromate, and we most certainly answered that question, 5.71 grams. All right, and then the last one, we have some potassium phosphate. At what volume in cubic centimeters of a 1.6 molar potassium phosphate solution is required to react with a solution containing 3.44 times 10 to the 24 formula units of nickel-2 chromate? And so once again, we have to look at the balanced chemical equation for this, and hopefully this time I won't forget to balance the equation. So we have potassium phosphate, that's K3PO4, plus nickel-2 chlorate, that's NiClO3 2, and this is another double replacement. It's Ni, not N. N is nitrogen. And we get potassium chlorate, KClO3, plus nickel phosphate, NaNi3PO4 2. And then we just need to balance this equation. And to make things quick, we have 2, 3, 6, and 1. And so now we just take our number of formula units. We're going to take that to mass. All right. Well, there's a couple things we probably should know. Should probably know that 1 milliliter is equal to 1 cubic centimeter. And then you should probably know that 6.02 times 10 to the 23rd of anything is equal to 1 mole. So we're going to take this formula unit, convert it to moles, go moles to moles, and then we're going to use this expression, 1.6 molar, 1.6 molar, which equals 1.6 moles per 1 liter, and we can take moles of this to volume, and so that makes things very, very simple. So we need all three of those conversion factors, if you will. So we start off with 3.44 times 10 to the 24th of the Ni2, I'm sorry, that's not true, NiClO3 2, and we know that 6.02 times 10 to the 23rd of the NiClO3 2 is equal to 1 mole NiClO3 2, and that 3 moles is equal to 2 moles of the potassium phosphate. And since we know the concentration, we can say that 1.6 moles K3PO4 is equal to 1 liter. And since we know that 1 liter is equal to 1,000 milliliters, and both of these are potassium phosphate, and we know that 1 milliliter is equal to 1 cubic centimeter. That's exactly what we're trying to find, is the cubic centimeters of potassium phosphate needed to react. And so we've gone through all those conversion factors, and we should end up with 238 cubic centimeters. So we went a little bit long in the video, but hopefully this helps you answer some of those questions. All right, thank you for watching.